Good morning, class. Welcome to another installment of Engineering 201 Statics lecture. Morning lecture, good morning. We're continuing in Chapter 4. My plan is to finish up Chapter 4 today, and then next week it would finish up Chapter 5, which really isn't anything new. Sort of pulling a bunch of stuff together. And then the following week we have our next exam. So we are working towards that. All right, how did we get here? Well, we dealt with forces in lots of different ways on the first exam. And then we moved into Unit 2, which was finding moments. And I mentioned at the beginning of the semester, there's really only two things you have to know how to do is sum forces, sum moments, to keep something and set them equal to 0, to keep something from translating or spinning, toppling over. So in the second unit, we're looking at different moments. We found moments about a point in 2D. Then we found moments about an axis. And then we found moments about a specified line using the triple scalar product, basically taking the R cross F moment and dotting it with the line of interest. And from that, we could find the moment in Cartesian vector form, and we could also find the direction cosines alpha, beta, and gamma for that moment. Moving forward here, we're going to learn about another moment, a little specific one called a moment couple, or a couple moment. And then we're going to look at some problems just to simplify when we have forces and these moments happening, and then deal with distributed loadings real quick, and that sort of finishes up Chapter 4. So I'll take a moment here to ask if there are any questions before we get started. Okay, we'll take that as all is good. Let's move forward. I have a little drawing here of someone not steering their car. It looks like it's opening or closing a valve. They are attempting to rotate that clockwise, or righty, as we'd say. So it looks like it's going to be righty-tighty to close that valve versus going counterclockwise, which would be lefty-loosey. That's how some people remember which way for a screwdriver. Okay. So if I draw the free body diagram of that situation right next to it, I'm going to have a force here, and I'm going to have a force here. It's like having your hands at the 9 and 3 positions if you're driving your car and you want to make a right turn. Now, the line of action of these forces, as we know, extend infinitely in both directions. So I could draw the forces up, pushing on it. I could also show them as pulling. But this is working here, looking similar to that drawing. And there's a center point here, and I could draw a diameter straight across, and we'd see that those forces are perpendicular to that diameter, but also parallel to each other. Parallel to each other. So this would define a couple, or give us a visual of what's known as a couple, because a couple is two parallel forces with same magnitude. Here we have F and F. Same magnitude and opposite direction. So they're parallel. That's important. Same magnitude and opposite direction. And that's literally what we have here. Since these have direction, forces have directions, technically we probably could make this a minus F. And that's what will happen in drawings. And what that shows is that they are basically, F shows that they're the same magnitude. and the minus F shows that one is in the complete opposite direction of the other. Okay? So where we're trying to go with this is we have these two forces. They're in a pair, right? That's what couple is, a pair. They're parallel, same magnitude, opposite direction. That's known as a couple or a force couple. We can also refer to it as a, here I'll put force couple, a moment couple, because it's going to produce a moment, or a couple moment. And the intent of this is to try to create a moment, make it moment C, about the origin. But how do we calculate that when we have two? Okay. Well, we would think, define that moment couple or couple moment or force couple. So that'll be, let's call that A. We just add up the R cross F about some arbitrary point. And that point can be, in this case, the origin. That could be the origin. So let's put some numbers on here just so we can solve this problem as we go. Let's have that distance of 1 meter. Let's make this 10 newtons. And in many cases, they will not give you, they will not write 10 newtons over here, even though I did, because if they write 10 newtons here and that's F and this is minus F, it's implied that that one is 10 newtons also. So that's another way we can see that it's a couple moment where we're given the force of one but not the force of the other, and that alerts us to that. So let's make this the origin there, O. We could find that by summing it, so we could call this the F up. We'll do this one as sort of the, so that'll be counterclockwise positive. So that becomes a minus 10 times a distance of 0.5 if we're taking to the origin, plus a minus 10 times 0.5 to the origin, right? This is the one on this side. This is the one on this side at that distance. They're both trying to go in a negative direction. So this would give me negative 10 if those are units of newtons, Newton meter, or 10 Newton meter, and draw it like that. So we can find that about any point. You know, I could put a point up here and we could find the radiuses and all that, or position vectors. So that determines the moment. We said we have a 10 clockwise there. All right, no big deal. Now, when this gets into three-dimensional problems like things like this, where it gets a little messier, it can be harder to find that a good point and solve it. So really, when we have two forces here, even though they're a pair, a couple, we're solving it with two steps. We have to find, you know, we have to find the moment of the one and add it to the moment of the other. And that can get a little tedious if we have a lot of force couples or couple moments. So what would be the second way we could solve this? The second way is to take the moment about a point on line of action, right? That's the line of action here. here's a line of action, and here's a line of action, is to take the moment about a point on the line of action of one of the forces. So in our example, we could call this over here, let's call that point A over there on the left. So in our example, let's take it about point A. Moment couple, counterclockwise positive, is going to be 10 times 0, because that's the one that goes straight through, plus a minus 10 times 1 meter. That gives us minus 10 Newton meters, or 10 Newton meters clockwise. And as you can see here, we get the same answer. We did the same number of steps. We did 1 and 2. But if we take it about the point, if we take this force acting about that point, we really don't have to do this one because we know the distance is 0. So this second process can be a way to simplify the math we have to do. All right, we take a force about a point on the line of action of on the other force. Now, when we do this couple moment, we end up getting a couple moment, or a force couple, or a moment couple. But what's important about this, I'll put it up here, is it's a free vector. A couple moment is a free vector. What does that mean? That means if I have this drawing here, let me just clean this up. If I have this drawing, I can replace these two forces with a couple moment right here that's 10. Or we draw another one. I could draw with a couple moment right here of 10, and those are equivalent. I could even have it here, right? There's the center, and I draw the couple moment out here in space as 10 Newton meters. These are all equivalent systems right there. Since it's a free vector, I'm never going to take a moment times a distance. I don't have to cross it with anything, not like with a force. The force, it matters where it is location-wise. So we need a distance or position vector to a point or axis or a line. With a moment, we're not going to cross it or multiply it with any distance. So we can put it anywhere on the drawing, as we've shown right here. I'll include it up there. We can put it anywhere in the drawing. So it's very important. A couple moments, a free vector. All right, so real quick, let's rehash that. If we're in 2D, the moment will basically be force times distance. And we'll get a magnitude, and we have to have a direction, and that direction is either going to be clockwise or counterclockwise. If we're in 3D, we have to find that moment by r cross f, like we did last week. And that will have a magnitude, or it can be in Cartesian vector form. And the direction will be from our alpha, beta, and gamma direction cosines. Then obviously if we have more than one moment, the moment total is just going to be adding up all those r cross f's, or force times distance, and we find the resultant or total. And we can say two couple moments are equivalent, meaning they have the same effect if they produce same moment. And we'll get to that point after we do a couple example problems here. All right, before we jump any problems, any questions on this whole moment idea? All right, let's do a real simple one pulled from an old textbook, an old homework problem. We're told that F is going to be 150 pounds. And that's the F down here. It also means that'll be the F up here, just in the opposite direction. The highlighted F and minus F in this drawing that I've just highlighted shows that they are a couple moment, or a force couple. They produce a couple moments. Sorry, they're a force couple because it's F and minus F. Okay. I could have just easily, or they could have just easily, instead of writing 200 pounds here, they could have called this F2 and that F2. And they would make it minus, but since they didn't, all right, they leave it as 200. So they could have made it F2 and minus F2, and then we could have been told what it was, but they chose to show it that way. All right, we're told to find resultant couple moment. I'll abbreviate it that way. And the problem states two couples act on the beam as shown. So we know that they're couples, but from the drawing, we should be able to discern that. Find the resultant couple moment. Again, the couple moment would be a free vector. All right, we are in 2D. 2D means we're just going to take force times distance. Since we have two of them, we're going to take force times distance and force times distance. And this will be the 200. Again, we're going to pick positive as counterclockwise. That's the traditional way of doing it. And we'll add up those two forces. So the only thing we have to be aware of is that we want to take the force about a point on the other force. So we're basically going to pair up these two, and then we'll pair up these two as we solve it. Okay, F and minus F are at angles. They have the nice little triangles for us, so we don't have to calculate the angles. So we'll have to use the components. Normally, what would be the sine and cosine? We'll have to use the components. And what we want to do is find a point that we're going to take each about. So we're starting with this one here. Now we're going to take one of the forces about the other force. One of the forces about the other force. Since we know this point, and I'll call it point A, we can locate that point in relation to the other force. We'll call that B up here maybe. We know that from B to A, I have to go over 4 and down 1.5. So we're going to take this force here and take the moment about point A, because point A is on the line of action of that other force. So this is going to equal 150. I have to find the x component. That's 4 over 5 using that little triangle. And then the perpendicular distance. That's going to give me the sort of the position, the force here, the component here. So I need this distance. That'll be times 1.5. That's the x component. And there's a distance that gives us the moment. It's positive because it is trying to rotate that way. Then I have to include 150 times the y component. And the y component is going to be up here. And we have to use that horizontal distance, which is 4 feet. And that is the y component that's also trying to go, excuse me, counterclockwise. So it's also positive. And that takes care of the moment for the F minus F pair. Now we want to look at the F2 pair. So plus, that's going to be F2, that's 200. And I need the distance from one force to the other. Okay, so I'm going to take this top force, about the distance about point A. So that's 200 times 1.5, but it is trying to rotate it clockwise. So I have to make that a negative, right? This pair is trying to go this way. This pair is trying to rotate that way. So hence the negative here. If I go through that mess, if I go through all that math, I should get 240 foot-pounds or pounds-foot. It is positive, therefore it is in that direction. Now again, in this one here, I don't have a y component of that force, so I don't have a second F times D. So this all means that if I redrew this beam, the equivalent system, which we're going to talk about in a few minutes, would be I could put 240 foot-pounds, come on, right there. Or I could put it right at the center. And the idea is it is a equivalent system. Now, why is it equivalent? Where do the forces go? Well, if I sum forces of these two, they're going to cancel to 0. If I sum forces of these two, they also cancel to 0. That's the unique thing about a force couple or a pair of forces that form a couple moment. If I sum forces on this beam, they all cancel. However, there is a rotational tendency, that's a couple moment or a force couple, of 240 counterclockwise. So this over here would be known as an equivalent system. All right, any questions about that one? That's a nice easy one in 2 dimensions. The only way to complicate it is to add more forces. All right, so let's move on to an example of a force couple in 3D. All right, we are given that the force is 50 Newton meters. 50 Newton meters. Since I have an F and a minus F, that tells me that I have a force couple. I don't see anything else acting on this. And what we're asked to find is the force couple or couple moment, the magnitude of it. So we're going to find the couple moment. Now, we're also told that this is sitting in the XY plane. So therefore, our moment looks like it'll be in the XY plane. The spin of it, moment axes, right? You take R cross F, it's going to spin about a line in the that because the distances are in the Y and the X and the forces are in the Z. All right, so let's start off. Let's just look at this again. If I sum forces here, I'll have F plus minus F, therefore it equals 0. So that pair of forces, that force couple, they sum to 0. They have no translational effect on that piping system. However, they do have a rotational. Even though the forces are pushing on the wrenches and the wrenches are applied at different points, it's the same force, equal in magnitude, opposite in direction. All right, so how are we going to find the couple moment? Well, we're going to have to add the R cross F because we're in 3D. But we don't have to do two of them. We don't have to do R cross F of each one. We can take R cross one of the F's as long as we are crossing at about a point on the line of action of the other force. All right. So we have to find a point on the line of action. Again, the line of actions are here and here. So we need to find some points. Let's find this point here, and we'll find this point and see if there's a one better than the other. We'll call that A, and that's B. Point A, if we follow this out and put it into meters, that should be 0.2, a 0.3, and a 0. And B is going to be a 0.368. Was that 0.8? And 0 meters. So we have to take one force crossing with the other force. Since this force right here is positive, it's going up, let's take that force crossed with the position vector that comes from that point. So that's position vector goes from A to B, right? And then we cross it with that F. So what we're looking for here in our three by three is IJK. Our position vector goes from A to B. So we take the B coordinate minus the A coordinate. We'll get 0.1, 0.5, 0. All right, that's our A to B. And there's the force. And our force vector, if we want to write this in Cartesian vector form, our force, at least on this side, is going to be 0, 0, 50 newtons, right? Because it's only in the Z direction. So that'd be 0, 0, 50. All right, if I went through that mess, I'm going to get 25 in the I direction minus, I think, 5 in the J direction, Newton meters. Check that. That doesn't seem right. Hang on. I'm going to do that math again. 0.5. No, that should be a 2.5, I think. Oh, if I put 50 in here, it's 25. That looks better. And the IJ is 0.1. That's 5. Okay. Yeah. All right. That looks good. That gives us the couple moment in Cartesian vector form. If I want to find the magnitude, I take the square root of the squares, and that should be, while we're here, 25 squared plus 25 plus 0 equals 650. And I could find the alpha as a cosine minus. That would be 25 over 25.5. Nope. Yep, that's right. Where's it in my calculator? Hang on, sorry. Times 25 equals inverse cosine. 11.3 degrees. Then we can find beta. We can find gamma. Right. Solution done. All right, that's just the math to finish it up. Couple moment in 3 dimensions. Force couple. Again, it's a free vector. So on here, if we had this assembly redrawn, we could just put in here, we could just have a line. It would be this and couple moment, and then it would just be this, right? And that's a free vector, so we could put that anywhere. And that would be a full-blown problem on couple moments in 3D. All right, questions on that one? All right, let's move into equivalent systems. I've already alluded to this. It doesn't look right. There we go. Equivalent systems. All right, I think I had one more comment about this one. Nope. All right, equivalent systems. Now we sum forces, and they have to equal 0 for us. A force, a net force, would cause something to translate. We sum moments, that equal to 0, so they don't spin. But if we had a net moment, it would tend to cause the body to rotate. Okay? Now, for an equivalent system, as we saw in the earlier examples, it has to have the same force resultant, and it has to have the same couple moment resultant. Okay? It has to produce the same external effects. And I'm abbreviating that. Meaning it has to have the same F net or F resultant, and it has to have the same resultant moment. If the setups or situations have the same, then it gives us the same or equivalent system. Okay? So let's look at a quick example here. Just a conceptual. I have a force down here. An equivalent system would be to have that force no longer there, but put it somewhere else on the line of action. on a line of action, so I could put it up here, and they would have equivalent external forces. Now, how can I move it up there? Well, I just can't add another force when I already have a force down here. I just can't add that second one. I need to add that force plus a counter force here of negative F. That way, this force plus that minus F give me 0, so it's as if I didn't add anything at all. And the result then would be I just have the force up here. And now, since that's on the line of action, we call F a sliding vector, right? Moments were free vectors. A force is a sliding vector, meaning I can move it or slide it anywhere on that line of action, and it'll have the same effect. It's it's this. If I have a doorknob there, I can stand here and pull on the doorknob, or I can attach a rope to it and stand back here and pull on the rope with the same force, and it has the same effect on the doorknob. It's being pulled. It doesn't know if it's being pulled directly in contact or from 10 feet away. This is known as the principle of transmissibility. You've heard it. You don't need to know any more than it just means I can translate or slide that vector along the line of action. Okay? And the result is that it produces the same external effects. The same external effects. Now, internally, it may change because down here, I might be compressing everything around this force. Now up here, I'm sort of putting all these under tension. So internally, there might be some changes, but the external effects, that's all we really are concerned about here in statics, is the same. Okay? Let's do another little more complicated equivalent system. Nope, doesn't want to do it. Oh boy. You wouldn't think my typing would be worse than my handwriting, but. All right, so we saw that we just slid that. What if we have that same object and the force now is here? And we want to find an equivalent system where the force is, say, over here. Okay, again, we'd have to put if that original force was here, we'd have to put the minus F with this positive F, and this F here would cancel this one, and then we could slide it there. However, that's over at some distance from that point. It's no longer on the line of the line of action of that force. So if we would slide it over there, we would now have to replace this whole thing with that new force that we moved, plus whatever the effect of that, from that moving it from the other point would give us as far as a moment. Now that's the general case that they put in textbooks that I really never liked. So let me put that in a little, I think, cleaner way. Let me just have a beam here. And we put a force here at the end, and it's at a distance d from this end. All right, so just have some beam. We want to move force to left end. we want to move the force to the left end, meaning I want to have this set up. I want to have that force over here now. Right, maybe I'm asked to find what the equivalent system is if I move the force there. Moving the force, if we sum forces to 0, we get the same force, right? There's no change in the force. However, moving it from this first location A to the second, if we're looking at this point here, the origin, this force sets up a moment, force times d, about that point. Because of its location here, it has a moment, or creates a moment, or sets up a moment about point O. So if I want to have the equivalent system over here, I have to include that moment. So our true equivalent system, if I slid that force over there, would be that force and a moment. Now this one over here in A is equivalent to C because I included the external effects of the force being at the end of the beam if I slid it over there. So in the end, what does it mean? If I sum forces and I sum moments and they still equal to 0 or give me the same result in this one and this one, we would refer to them as equivalent systems. Equivalent systems. So let's do a quick, maybe not so quick, but a problem on equivalent systems. Now this is a 2D problem, which are always easier. And we're told to find, replace the force and couple system. All right, there's two forces there, and I see a couple moment, that's the 8. By an equivalent force, that means a single force and couple moment at point O. So we need to find a resultant force and moment couple or couple moment at the origin. All right, here's the origin. There's force 1, there's force 2, and there we have the couple moment. So what I'm really trying to do here is move forces to O and find that resultant couple moment. By finding an equivalent force and couple moment, I'm trying to move all the forces to O, which means I want to know the resultant force. And then I have to find the resultant couple moment at that point also. All right, let's start off. Let's deal with the force. The force, we're really finding the resultant, so I want to sum forces in the x direction, positive to the right. I'm going to have 6. Its component horizontally is going to be 5 over 13. Positive direction. The other force is a force. It's minus 4, and that's at cosine 60. And if I go through that, I get about 0.3 kilonewtons. So it's 300 newtons. Positive, so it's that way. All right, some forces in the y direction, positive up. 6, that'll be 12 over 13. Minus 4 sine of 60. That should give me a point, about 2.1 kilonewtons, and that is up. Now I want to find the resultant force. I want to draw one force, so I have to put that in, take those two components, find the resultant from that, magnitude and directions. So resultant is going to be the square root of the squares. And if I go through that, I get about, I get a little over, well, this is 2.07. This one comes out to be about 2.1 kilonewtons. I changed that because you can't have 2.1 and 2.1 as a hypotenuse and one of the short legs. All right, the angle, inverse tangent, the y over the x. Since they're both positive, we expect that to be in the first quadrant. That comes out to be about 82 degrees. So if I was redrawing my equivalent system, there would be the resultant force at point O. Okay. All right. How do I find the moment? To find a moment is force times distance. I have to use the components of these green vectors. I have to remember to add the 8. So the moment at O is going to be counterclockwise positive. That's the 8, right? Can't forget that one. That's a free vector. We include the direction, which is positive. Minus 6. That's 12 over 13 gives us the up components. We need the distance across that, which is 4. Plus the 6 component, that's giving us this component. Now we want this one. 6 times 5 over 13. That's the force this way. We need that distance. That's a distance of 5 meters. The components of this one are down and over. We're not going to worry about the y component because it goes right through O. So we're going to have 4 cosine of 60, and that has a distance of 4 meters. I go through that. I get about a minus 10.6 kilonewton meters. So if I was going to draw that over here on our drawing, because that's clockwise, I would do this and put 10.6 kilonewton meters. And that's the single equivalent force and couple moment about point O in the upper right there. That would be the box for that. All right, questions on that really nice problem. I like that problem a lot. I'm going to do that to remind me that I like that problem a lot. Hint, hint, say no more. All right, that's been in 2D. Any questions up till now? All right, let's move into a 3D problem. We're getting close. The last couple slides here go and problems go fairly quickly, so just hang on. All right, how do we know this is in 3D? Well, we see our axes set up there. There's our X, Y, and up here's our Z. And we are given the forces in Cartesian vector form. We don't see any couple moments here, but we're given 3 forces and they're in Cartesian vector form, which tells me that this is a 3D problem. We are told in the problem to find the resultant force at A and the couple moment at A. So A is basically the origin. And it's more of not find that equivalent force and couple moment, but replace the force system, the system of these three forces, with an equivalent resultant force and couple moment. Now, don't complicate these problems. Don't make them harder than they need to be. If I want to find the resultant force, what do? Just like we've done all semester, I add up all the forces. And since they're already in IJK, I just have to sum everything into IJK. So if I look through that, I'm going to have, I can sort of probably do this in my head, 400I, what's that, minus plus 300J, and let's see, minus a 5, minus 1, minus 650K. Done. Done, done, done. That was easy. I love it when they give it in Cartesian vector form. We just have to add them all together. That's the resultant force at point A. Now, that's really the resultant force on the whole system. The way we move it to point A is now include the moments that are set up by each of these individual three forces and add that at A also. So we're going to need a position vector. It goes from here to here, and we're going to need one to go from there to there. I think that's B up there. We can call this point C. So from A to B, see if we can do that in our head. From A to B, that's going to be 0, 0, 12. That's an easy one. From R to C, position vector, that'll be 0, minus 1, 8. Okay. Now, let me just show you something here, a little hint. The line of action of this force over here, this one at C, goes vertical. So I could use position vector from A to E because it does cross that force instead of going from there to there. That one would be even easier as 0, minus 1, 0. That makes it even easier because there's going to be less in the 3 by 3s there. Everybody okay with that? I can use a position vector goes anywhere on that line of action, but A to E right there, come on, is certainly the cleanest and simplest. All right, so let's find the moment. Resultant couple moment at A. We're going to add up all the moments at A due to those three. So that's going to be from 1 to 3 forces. So let's sort of build those together. IJK. Let's go with force 1. Force 1 is down here is 300, 400 minus 100. We're going to use from A to B there. So that's going to be 0, 0, 12. Okay, let's find a moment due to this force about point A. Let's find the next force. The next force is 2, so that's going to be 100 minus 100 minus 50. We're using the same position vector, A to B. So that's a 0, 0, 12 there. And this last one, we're using the F3, which is 0, 0, minus 500. And we're going to use this position vector because it's a lot easier. That's 0, negative 1, 0. So summing the forces here gave us the resultant force. To move it to point A, we have to include the effect of the moments it created where they are currently before we move it. And if we go through all that, we get minus 3100 I, about 4800 J, and 0 K Newton meters. And that's as far as it asks us to go. However, if it asks us to find the magnitude, that's the square root, and we could find the angles by doing inverse cosine, we could continue that problem and make it a big, long, ugly problem. But this one wasn't too bad, I don't think. All right, so we just found the resultant of a force and couple system, meaning one or more forces and one or more couple moments, any combination of those. Questions there? All right, let's talk about this idea, further reduction. So we just reduced, or I don't know if we reduced, but we reduced the forces and couple moments to a single force, single couple moment. Okay, single force, single couple moment. What we want to do now is see if we can further reduce it, and this is reducing it to a single force. And not quite yet. All right, single force. Let's look at this setup. I have a beam here. I have a force acting, and it's got, there's a moment, and that's the origin. Let's say that originally came from this. I had a couple forces, I had a couple moments, bunch of mess, and I cleaned it up to do a single resultant force and resultant couple moment at O, right? That's sort of what we did here in those last problems. Let's say we got ourselves to this point now. We have a single force, single moment on the body. If I take that force and slide it from its original position some distance, it could be an equivalent system since I had the same force, and since I moved it that distance, it sets up the moment, because this moment, is some forces times distance. So summing forces, I get the same thing, and summing moments, I get the same thing. So once I get into a single force and single moment, now I want to slide that force. So maybe it can be a single force acting at a different point. So how do I do that? Well, moving the force is pretty easy. The force will be the force, right? Resultant force is the resultant force. I don't change anything but the location. But what I have to do is set up that resultant moment over here. I set equal to that resultant force moved to that distance. And the idea is I can find where to move that force to have an equivalent system of a single force. Okay. Maybe easier if we do this, or I show you this through an example. So here I have what's known as a simply supported beam, meaning it has a pin over here that's like a hinge, and it's just sitting on a roller here. So if it expands or contracts due to temperature, it's not going to buckle or compress or stretch. It's like a roller there, just something that'll allow it to extend and contract if needed without affecting, the internal stresses. So we want to replace these three forces and couple moment with a single force. With a single force. All right. How do we start this? Well, we only know how to do two things, sum forces and sum moments. Okay, so we're going to sum forces to get that resultant force. Since we're in 2D, we have to find the x component here. We'll call positive to the right. That'll be 450 cosine of 60 is the first one, nothing for the 300, and minus 700 sine of 30. That gives us about 125 that way. All right, three forces, 1, 2, 3, and then couple moment we have to remember there. All right, so let's find the result in the y direction. Positive up, that's minus 450 sine of 60, minus 300, minus 700 cosine of 30, and that gives us 1296, I think, down. Now, that's just the general effect of those forces. I haven't moved them or done anything yet. Now, I can go here and find the resultant and the angle, right? That's inverse tangent of the y over the x. That's square rooting the squares. And if I go through all that mess, I get 1302. That's going to be at about 84 degrees down this way, third quadrant. And we're just going to save that for later. All right, what about the moment? How do we deal with the moment and then find the location? We want to specify the force. To see, the problem says replace the loading acting on a beam by a single resultant force. Specify where the force acts measured from B. Measured from B. All right, so we have the resultant force. We're going to set up the resultant moment at B equal to all the moments set up by those three forces at B. Okay. On this side, we have that 1296 because this one doesn't, that component does nothing about a moment about B because they're all going at that level. There's a zero distance. So on this side, it'll be 1296 times x. That's the distance from B. And that has to equal the moments that are all set up by B. Now, we don't want to forget the 1500. So I'm going to put that in first. And I'm going to include all the other forces. Now, since I made that one positive because it's down, we're really solving this for positive this way. Okay. So the 450, we want just the y component. We don't need the x. That's minus 450 sine of 60. That's at a distance of 4 meters. All right, that's trying to rotate it this way. We can put the 300 in there, but that's at 0 distance. The 700 will be the cosine 30 vertical component. Its distance is 3 meters. So that accounts for all 3 forces plus the moment. If we go through and solve for x, whatever that mess is over 1296, we get 1.4 meters. Since that's positive, it'll be to the right. So the resultant force, single force at a location, is the 1802 at 85, and its point of application is 1.4 meters over. So about there. There's our resultant force. Now that problem shouldn't be too difficult to follow. It's just the last step of setting up that moment down here to find the distance. Okay. Now another way, as you're doing this, we solve for the resultant force. That's all the same. When we do the moments, maybe we find the equivalent moment about B, and then we can set it there. All right, questions on that problem? All right, let me just introduce this one idea here fairly quickly, and then we're going to finish up with distributed loading. The idea of a wrench. All right, here we are in 3D. Let's say I have a moment that spins like this. A result moment O spins like that. That would be positive direction using your right hand rule. Spin our finger, stick our thumb up. There's my wristband. So there's the moment axis. There's the plus moment direction. Now, if we happen to reduce that force, and we have the moment about O, and the force ends up, let's say, being out here. It's at some angle, essentially, to that z-axis. Because that's a 3D problem. It's very possible. Resultant force from summing, resultant moment from that, we find them all at point O. Now that force is at an angle, so I could find the component of that force in the k direction right there. If I have that situation where I have a force that is surrounded by a moment, that is referred to as a wrench. It's more like a screw. This would be, there's our screwdriver. And since it's spinning that way, that would be righty-tighty. And we'd be pushing that way at the same time. So we're basically pushing and rotating. It's like we're pushing the screw in. So this is known also as a screw. first a wrench, but it could be also a screw, which I think makes a little more sense. Wrench, not so much. Screw, I kind of like that idea. Just the sort of the force is pushing up as you're rotating at the same time. Okay, and that rarely happens. I just want to give you that. All right, last little piece of lecture here. And then one quick problem. And we are done. Now I'm just going to carry this problem, carry that over here to look at. Oh, wrong one. Okay, not going to do it. All right, up until now, let's say we had the beam here. We could have some forces acting on it in a couple moment, called F2, F3, F1. And they were thought of as to be point loading. Basically a force acting at a point. It's like pushing your finger onto the desk. But even though you have some width of your finger, we take that force to act exactly at that distance or at that point. But there are many situations in real life where maybe on that beam we have a pile of sand or a pile of snow and ice, or we have a sign that's set up and there's wind blowing on it. Or if we have a dam here and we have all this pressure from the fluid. Those are known as distributed loading. We typically will draw them with arrows. Right, there's the arrows. This one would be drawn like this. Those are awful arrows. This sign would be this. The dam here would be that. And we use arrows for the direction of intensity. And we refer to this as a loading function if we're told what it is. All right, we might be told what the weight function is or the loading function for that, Wx, which is kind of like pressure. This would be thought of as a load intensity diagram. And what we need to know is, where do I draw the resultant force? Is it sort of here in the middle? Is it near the bottom? Where do I put that and what is it? Okay, what is it? Now, if they are simple shapes, and that means square, rectangle, triangle, the resultant force of that loading equals the area under the curve. The area under the curve. So for these, it would be length times width. For the triangle, it would be half base times height. Basically find the area. So, this one probably would be pretty easy, length times width. This one more has this shape, so it's more triangular. But what if we have functions? So one type of function would be this. The function to get the resultant force is we have to integrate that function. And when we integrate that, we should know from calculus we get the area under the curve. So if we have a setup like this, even though that's not a common, we could break that into common, meaning we could have a rectangle here. And here we have a triangle. So we would split it up into two different areas, two different forces. Whereas that, if we had a function on there, a curve, we would have to integrate that to get our resultant force. And then we can find, once we have the resultant force, we can find the location of that resultant force by basically summing the moments divided by the force and solving for that distance. And we'll do that in a problem here. All right, so let's do an example here. We'll do one. These are simple. Did we lose? There we go. We'll do this simply supported one, and then we'll do a second one where it's going to be an example with a function. All right, so we look at this loading. I don't know if it's a pile of boxes across the right and then a triangular box, but it's distributed loading, meaning it's distributed over a lot of points. The direction of the arrows tells us it's down. Okay, so it's some weight on top of it. So we're going to treat this as a simply supported beam with a rectangular function there and a triangle function there. So we want to find the resultant force and couple moment at the origin. That's what we're asked to find. So how do we do that? Well, resultant force, we have to sum forces. Resultant moment, we have to sum moments. We've been doing that, or will do that the rest of the semester. So let's find for this one here. What's the area here? Well, okay, not sure what's happening. I keep getting stop sharing my screen. I'm probably clicking something, but see if we can get through that. All right, that resultant force there for, we'll call it 1, is length times width, which is going to be length is 4, or length times height, and that height is 200. So that has 800 newtons of force that's combined in that green area. For the yellow area, that's a triangular shape, so that loading is half the base, which is 3, times the height, which is still 200 over here, because it's 200 there. And that gives us 300 newtons. So if we sum forces, that's pretty easy. We're picking positive down because all the loading is down. We could pick positive up and they'd all be negatives and we change the direction, but since everything's down, that's 800 plus 300, that equals 1100 newtons. And I'll just put the down arrow there to remind us. So if we have this beam here and it's simply supported there by a pin, there's a roller, and we want to put that force there at O, there's 1100 newtons. All right, let's find the moment. Result moment O is adding up all the moments about O. There'll be 2 of them because we have 2 regions, 2 distributed loadings. Counterclockwise positive, that means minus 800. Now, where does that distance, where do we put the distance of that? When we have a simple shape like that, it will go right in the middle. So if it's a rectangle, we put it at half and half. So that's a distance of 2. Basically, the force goes right through the centroid. And the centroid of a rectangle or square is right in the middle. Plus the triangular, the yellow one, minus 300. What is its distance? Well, with a triangular shape, we want to go right through the centroid. And the centroid is at 1/3, 2/3. It's 1/3 from the 90-degree corner. 1/3 over 2/3. Now, we have to be careful. We just don't say, well, 1/3 of that 3 distance is 1. Yeah, that's true. That's 1 meter, and there's 2 meters. But that's not the distance. Remember, we're taking the moment about O, so we have to use this distance here to here. And that's going to be the 4 meters plus the 1 meter of the triangle. That's the #1 mistake students make with these type of problems. They do half of that as 2. That's great. They do the 1/3 of that. They say it's 1, but that's incorrect. It should be 5. If we go through that, we should get 3,100 Newton meters. That's 3,100 negative, so that's 3,100. There we go. Sorry about that. 3,100 clockwise. So if we're replacing an equivalent system up here, we'd say 3,100 Newton meters. And that would be our solution. I want to take this problem one step further and find that single resultant force of 1,100. Where do I put it so I can just have a single force? Meaning I'm going to slide that force this way some distance so it equals that 3,100. So I'm going to set the resultant moment equal force resultant times distance. That's 3,100 equals 1,100 times d. And that gives me 2.82 meters. Meaning, if I slide this out, if I now slide this force out, I would just have a single force at that distance. I think my computer is telling me it's getting close to the end here, which it is. Almost there. Come on, share my screen. There we go. That would be the single force if we did a single resultant. All right, I want to try to give you one last problem here to do that function so you can understand it, so you can see it. Function distributed loading. See if it's going to let me do this before it shuts down. All right, let me draw this real quick. Let's say we have a simply supported beam. It's sort of like a deck. We'll make it 10 meters long. That's a big deck, but that's fine. Easy numbers. And we're going to put a function on here. We're going to have a loading, and it's going to be a pile of snow or something like that. And I don't know what it looks like, but I'm going to draw it like that. And we're giving the weight function. And that weight function is 300x minus 50x squared plus 0.3 x to the fourth pounds per foot. All right. I don't know if we're going to make it through this problem or not, so I may talk through it real quick. All right, how do we solve this? Well, we can't use the simple shapes. That resultant force is going to be integrating Wx dx. Try that again. And I'm going to do that real quick so we don't get kicked off here. That ends up being 150 if I reorder at 150 x squared minus 50 x cubed plus 0.3 over 5 x to the fourth. And we're going to evaluate that from 0 to 10 because that's the entire length, right? That's going from 0 to L. If we do that, we get 4330, or if you do that, so you can check that offline. Now we want to use that resultant force times some distance equals the resultant moment. We just found that as that. And my screen keeps not wanting to. I'm going to keep trying. So to find that distance, it's going to be the resultant over the force. We just found the force as the 4330. How do we find this moment? Well, the moment is going to be the force times a distance. A force times a distance. So we're going to integrate from 0 to L x times this function. And if you go all the way through that, you should get 25,000 over 4330. That gives us 5.7 feet. So that's the loading, and that's where we replace that. Trying to do this real quick. That's meters, I think. No, feet. That will be a resultant at that distance of an equivalent system from that function loading. Now let me go back here. That has to be a dx. Make sure you didn't miss this. This is really just x times fr, right? Fr is this. If we integrate it, x is that distance. So we just put an x in there, dx. We can solve for the moment due to that loading and divide by the resultant force, and we can get the distance for that force. All right. Went through a lot there. That gets us through chapter 4. And finishes up. Let me do this last page here and ask if there's any questions on everything that I blew through today. All right, it doesn't want me to stay on sharing my screen, so any questions? Couple moments, reducing it to a single resultant force in couple moment, and then a single force, and then dealing with distributed loading. That should get you through. That should get you through in the unit 2. That should get you through class the rest of 7 and finish up 8, which means next week we'll do class 9 and 10. It's not really a lot of material. All right. Not even sure you still hear me now because my screen has begun to lock up.
I'm good. Thank you.
Now we're back. So any questions? If everybody's good, I'll just hang out. Otherwise, have a great day. Looks like another warm one here on the East Coast. Kind of strange when it's almost 60 degrees out and there's snow everywhere. So, but we'll take it.
All right. Thank you. Have a nice day.
Okay, I'll assume everybody's good. I see people are leaving. Have a great day. And I'm going to stop recording now.